our next topic is self-induction. So in self-induction, what happened is there is a coil, suppose we consider the coil here. Then through this coil some amount of current is allowed to flow. This one, okay, this is the coil, and there is a battery, there is a key. So when the key is switched on or key is closed, then current in the circuit starts developing. Now we know that when current flows through it, then through the coil there will be change in magnetic flux. The reason is that it's a solenoid like coil, and we know that the solenoid, when current passes through it, it becomes like a magnet, right? So if it becomes a magnet, field lines will generate from one side and then it will enter in the other side. Suppose like this, suppose this side has become north, this side is south, so field lines will go like this, then it will enter through south, and then it will complete the cycle from south to north inside the solenoid. Or in other word, through this solenoid, inside this there will be some magnetic field lines. Now due to this change in flux, how flux is changing? Initially there were no current, so flux was 0. Then suddenly current in the circuit developed, so there will be some flux. So that means flux is changing from 0 to a certain value. So due to change in this flux in the coil, there will be induced EMF. Okay, and this process is called self-induction. Why self-induction? Because current is flowing in the coil itself, and the induced EMF is also produced in the same coil. So it is a self-induction. Now we know that that induced EMF which is produced, that induced EMF will oppose the development of current in the circuit, right? Because we know what is the nature of induced EMF by Lenz's law. The nature of induced EMF is such that it opposes the main cause of induction. So here what is the main cause of induction? Development of current in the circuit. So the induced EMF which will be produced, that will oppose the development of current in the circuit. Again when the switch is off, suppose initially it was in on state, now it is off. So off means now the current will decrease from a certain value to 0, and we can say that the field lines will again change, suppose from a certain value to 0. Okay, then during this change also there will be induced EMF again in the coil. And what will be the nature of the induced EMF now? Because it opposes the cause of induction. In this case, what is the cause of induction? Decay of current. Decay means reduction of current. Current is reducing now from a certain value to 0. So this induced EMF produced, it will oppose the reduce in current, or it will oppose the decay of current. Okay, that means when current is developing in the circuit, then induced EMF will try to oppose the development of current. When current is reducing in the circuit, induced EMF will oppose the reduction of current in the circuit. So that is why in both the process it will take some time to get the maximum, or to attain the maximum current level. It will take time. Again, to become the current minimum, it will take some time, because induced EMF is opposing in both the processes. Okay. So anyways, here what happened is, this induced EMF, how we will get the expression for that? In this particular case, the phi means the flux linked with the coil, is directly proportional to the amount of current flowing through it. Suppose I current is flowing through it, and how much flux is developed? Phi B for magnetic flux. Now from this proportionality sign is removed by equal sign. There is a constant L. The name of this constant is coefficient of self-induction, or we also call it self-inductance. The unit of, or the SI unit of L is Henry, or in short we write it by H. Okay. Then induced EMF. Induced EMF is minus d phi dt by Lenz's law. So here minus d dt of phi means Li, this value. So L is being a constant, it will come out minus L, and inside differentiation we have di dt. So E equals to minus L di dt. This is another expression for induced EMF for in a coil. Okay. Now dimensional formula of L. This one you remember, dimensional formula of L is m L square T minus 2 A minus 2. How it came? For that you have to analyze the formula. Okay, roughly I have done here. Suppose I started with this formula. Then E means it is EMF. EMF is nothing but physically same with voltage, no? So voltage means what? Work done by charge. Potential means work done by charge. W by Q minus L. Then I means ampere is the dimensional formula under bracket A. T under bracket capital T. Work done dimensional formula is ml square T minus 2. Charge dimensional formula is current into time AT. Okay, so from this T get cancelled. Then this A will come down here, so A into A becomes A square, and this side we have L, whose dimensional formula we are finding. So this A square means A becomes A square. This A square will go up and it will become A to the power minus 2. Okay, so finally what is the formula? ml square T minus 2 A minus 2 for L. It's written there. Okay, now how to define self-inductance. So to define self-inductance, again we will take help from this formula. See here, self-inductance L becomes equal to EMF provided the value of di dt becomes unity. In this way we will define. So here I have written self-inductance is defined as the induced EMF, means L becomes equal to E, produced in a coil if the rate of decrease in current is unity. That means di dt minus di dt is 1, means magnitude is 1. Okay, why decrease I have written? Decrease is taking this minus sign, no, minus di dt. So that is why I have written decrease of current becomes unity, means this term becomes unity, means 1, then L becomes equal to E. Okay, this is the definition of self-inductance. Now definition of 1 Henry, that is also same means we'll start with this formula. L is equal to 1 Henry when E equals to 1 volt and di dt is, how much is that? 1 ampere per second. 1 ampere per second. So in word what we will write? That the self-inductance of a coil is 1 Henry provided the induced EMF developed in it is 1 volt, and when the rate of change of or when the rate of decrease of current in the circuit is 1 ampere per second. Okay, so this is the definition of 1 Henry. Now we will find out an expression for self-inductance for a solenoid, especially for solenoid. Okay, suppose there is a solenoid. Through this solenoid I current is flowing. The length of the solenoid is L, suppose. Okay, now we know that in a solenoid what is the value of magnetic field? We already deduced this expression in chapter 4. B equals to mu naught Ni. What is N here? Small n. It is not the number of turns, but it is number of turns per unit length. So if L is the length, okay, and capital N is the total number of turns, so total number of turns by length will give us N, because N means what? Number of turns per unit length. Okay, so from this N into L, small n into L gives us capital N. So that's what I have written, this one. Now flux, the expression for flux, total flux linked with this coil. So total flux will be magnetic flux linked with each turn. With each turn how much flux is related, that one, into the total number of turns. That will be the total magnetic flux linked with this whole coil. Okay, now magnetic flux linked with each turn. For magnetic flux we have the formula BA. Actually it is B dot A, but in this cases B and A are in the same, this one, no, B and A will be in the same direction. So if it is in the same direction, angle will be 0 degree. So it will be B dot A becomes equal to BA then. Okay, so anyways, magnetic flux, in place of this magnetic flux we'll write BA. That's what we have written here. Yeah, this one, into number of turns, means capital N, or equals to what? NL. Now B means this one, this B we are substituting it here, and A, like A only. Okay, then you in place of phi B we can write Li. Can we write, just to see? phi b means Li, no? This one phi b equals to Li. Okay, this one we have used here because we are finding an expression for L, self inductance. So from this you just simplify, you multiply, we are getting this value n, and n becomes n square. Then this I and I get cancelled and we get the expression for self inductance, mu naught n square Al. Okay, or we can express it in this way also, in terms of capital N, because see, n square, n means what? Capital N by L, no? So in place of small n we can write capital N by L square and if you do so, 1L get cancelled, this one, no, this becomes L square and this is 1L, so as it gets cancelled, below we have only 1L. So finally the expression for L becomes this one. Both the expression you can write this one or this one. Then combination of coils. Just like combination of resistances, we have series combination, parallel combination. Here also same way we have series combination of two inductor. This type of coil, this one, no, this type of coils are called inductors. So these two inductors, they are connected in series. The first one is in series. So since they are connected in series, same amount of current will flow through them, because we know in series current is same, but yes, their EMF will be different. So induced EMF developed across this is suppose E1, across this E2, it is written epsilon, no? Okay, epsilon 1, epsilon 2. Then you can write it like this also, E is equal to E1 plus E2, induced EMF. Okay, and this also correct. Then the self inductance of the first coil is L1, self inductance of the second coil is L2. Now current flowing is same. Okay, so if same current is flowing, we know for induced EMF we have a formula that induced EMF is equal to L minus L di dt. This induced EMF is minus L di dt. E1, we are talking about the first coil, so it will be minus L1 di dt. See here, I is common, this one same I, because same current is flowing as they are in series. Now for the second coil, what will be the change? Only this will be minus L2, but this term will remain same. Okay, now this di dt get cancelled. Since all are negative, we can make every, so we can multiply it with minus and then the whole thing becomes plus. So what will remain? L equal to L1 plus L2. So it's like series combination of resistances. What is the equivalent resistance? R equals to R1 plus R2. Similarly, L equals to L1 plus L2. Okay. For series, this is for series. For 3 coil, there will be another term like plus L3. For 4 plus L4, it goes on like this. Then for parallel. So for parallel combination, we know that the current changes but the EMF remains same. So since current changes, the thing becomes like this. Suppose the total current is I. At this point it is dividing. I1 is flowing through L1, I2 through L2. So this coil is having a self-inductance L1, this is having a self-inductance L2, and finally again both the current combines here at this point, and then total amount of current coming out of the coil is also I. So here can we write I is equal to I1 plus I2, because I is splitting up into two parts. So we started with this formula. Now suppose we know di dt, we are differentiating it with respect to time, this formula. So what we'll get? Di dt equals to di1 dt plus di2 dt. Then we have this formula. So from here di dt equals to what? Minus E by L. So in this place di dt we can write minus E by L. In this place what we can write? Minus E by L1 here. Can we write? Because this is about the first coil, and E will be same or epsilon will be same because they are in parallel. So that's what we have done. In place of here, in place of di dt, we'll write minus E epsilon by L. In place of di1 by dt, we write minus epsilon by L1. di2 by dt is minus epsilon by L2. So these things we are writing in this equation, this one, okay. So from this epsilon minus epsilon, if we take common, this will be 1 by L1 plus 1 by L2. So this minus epsilon and this minus epsilon get cancelled. What we get? 1 by L equals to 1 by L1 plus 1 by L2. So this is the expression for parallel combination. It's like 1 by R equals to 1 by R1 plus 1 by R2. Or if you take LCM, you'll get this. Otherwise, till this step also it is alright. You can keep it like this till this step. Okay. For 3 inductors, there will be another term 1 by plus 1 by L3. And that way it will go on till n. Okay. This one, energy stored in an inductor. Okay, energy stored in an inductor means, suppose we know that when current develops in a coil, suppose we have this coil, okay, current is developing in the coil, so there will be induced EMF, and we know induced EMF will oppose the development of current in the circuit. So that means when a small current is developed in the circuit, suppose di, then already there will be some induced EMF. How much induced EMF will be developed in the circuit for di development of current? It will be this one, no? This will be the induced EMF developed in this coil. Okay. Now further, if you want to increase the amount of current, then you have to do some amount of work against this induced EMF, because induced EMF will oppose the further increase in current in the circuit. So the work that we are doing to develop a certain amount of current in the circuit, that will remain stored, or that will be stored in the inductor in the form of potential energy, and that energy we are finding here. Okay, stored energy or potential energy that we are finding. So here we are starting with this formula. Suppose initially di current is developed in this coil. As a result, induced EMF related to the coil will be this much. Now suppose again we want to give some more charge to this. How much charge? dq charge. So if you want to give dq charge against E, we have to do some amount of work. What is that work? dw, small work done. We are doing, why? Because we want to develop dq current, dq more current in the circuit. Okay, dq more charge in the circuit we want to give. So we know that work done, just now while discussing the dimensional formula of L, I told you that work done is equal to, one second, EMF is equal to work done by time. EMF equals to, or this implies, sorry, charge, work done by charge. Okay, or this implies EMF into charge gives us work done. So that's what we have done. Work done is equal to what? Induced EMF into small charge, that is that we want to provide in the coil. Okay, now from dw, if you want to get the total work done, we are supposed to integrate it to get w. But before we go for integration, let us substitute some values. Here in place of E, we have substituted L di dt, this one, neglecting the negative sign as we are using the magnitude only. Okay, dq will remain as it is. Now this part dq by dt, this part, this is nothing but current. This one, no, dq by dt is what? Current. So since it is current, next step what it will be? This will be L di, and this will be I. Okay, then we are integrating both sides, dw and this side also. So as we integrate, we will get integration dw, in right hand side integration L I di. Here we are writing di, I mean I. Okay, this is I, no, this one I. And di we have already. Now this L being constant, it will come out of the integration. This side, after integrating, we will get w. In right hand side, L will be outside. Inside integration we have I di, means it is like x dx. So integration x dx is what is that? It is x square by 2. So it will be I square by 2. I square by 2. Okay, And limit means suppose from the initial point means 0 till a certain value. Suppose the maximum current that we want to develop in the circuit is, or in the coil is I naught. So your limit will be from 0 to I naught. Okay. Then you substitute lower limit, upper limit minus lower limit, means this I, once it will be replaced by I naught, so it becomes I naught square by 2. Then it should be minus lower limit. The lower limit is 0, so the 0 square by 2 means it is 0 only, so you don't have to write that. Okay. So finally what we got, half L I naught square. This is the expression for work done. And if this is the expression for work done, we know that work done and stored energy will be same. Whatever work we are doing, that will be the stored energy, or that will be the potential energy. So instead of writing W, we can write U. U equals to half L I naught square. This is the stored energy in the inductor. Okay, or stored in the magnetic field of the inductor. Anyways, then this is one expression, obviously this one. We can modify this expression from this formula we have. Okay, mu naught n I, there it was I, but here the maximum current is I naught, so we modified this equation in the form mu naught n I naught. So from this, I naught equals to B by mu naught n. Okay, and for solenoid we know the expression for L is this one, we had already derived this. So this value and this value we are substituting in this equation, so it becomes half L means this one, I naught square means this square, and if you do the calculation, the value comes as this. This is another expression for magnetic energy. This is called magnetic energy also, UM, or stored energy, whatever you say, or potential energy. So another thing, this one, magnetic energy density, this part. Magnetic energy density is nothing but this magnetic energy divided by volume. So see here, AL, A means what? Cross sectional area, L means what? Length. So area into length gives us volume. So if this is volume, if this volume we bring it down here, it will be energy by volume, which is called magnetic energy density. Okay, simple thing. So energy by volume, if we do in left hand side, in right hand side what we'll have? Only half B square by mu naught. So half B square by mu naught is the expression for magnetic energy density. Means it is energy per unit volume. Okay. Then in next video we'll discuss about mutual induction and mutual inductance.